Everyone. So it has been quite a while since I left MIT. So the last talk I gave at MIT was actually my PhD thesis defense talk. So it has been 2.5 years ago. So I guess, so how time flies. So many of the thesis committees are online today. So it feels like a thesis defense talk again. But I guess the difference between this talk and the thesis defense talk is that I only need to acknowledge my hardworking student at the end. Okay, so let's get started. So today I will talk about the recent work that in my group on pioneering the understanding of generative model. So we try to invert the real image into the latent space, then we can facilitate the real image editing applications. So recent years, there is great progress for image synthesis. So starting from 2014, the GAN proposed and people improve over that. And we have the STEL GAN v2 last year that can synthesize the object and scenes in different angle and perspective. So here we want to get into the representation learning. So we want try to understand the deep generative representation. So after training, so this generative model is just a convolutional network. So giving a random vector as input, you throw into the generator, then can synthesize lot of image. So when we talk about understanding the internal representations, so usually we are talking about two kinds of latent representations. So the first latent representation is latent units. So those are the convolution filters. So as our previous work, like my previous work at MIT, so we analyze the semantic of those units in those scene classifiers. Then David further push these directions to understanding the filters in generative representations. So another kind of representation is a latent space. So for the latent unit understanding, so David has this wonderful work on GAN dissection that we can align the semantic labels for the internal units. So then we can turn on and turn off the units to achieve such interactive editing. But here I want to focus on interpreting the latent space, because you can see the latent space is actually the driving force behind all the variations. Now, how to better understand the feature vectors in the latent space is a much less explored topic. So we can have some visualization about latent space. So here is a random walk in the latent space of a generator to synthesize the bad rule. So each time we just add some increments on the latent space, then the output battery images will change accordingly. So from this random walk visualization, you can see this latent space actually encodes a lot of interesting semantic attributes, such as the number of beds and the single bed, and also the perspective, the rules, also the lightning conditions, and the shape of the different object inside, such as cabinets and lamp. So there are a lot of semantics that encoded in the latent space. If we can discover those latent space, then we can control those synthesized image based on our requirements. So for scene understanding, so we have worked on scene understanding for quite a while. So scene compared to object, the scene is much more complex. So there are multiple level of scene descriptors. For example, giving this particular input image, we can use those image labels to describe the scene, such as this is a bedroom. There are a lot of scene attributes like nature, lightning, woods, and foliage. We also can have more like 2.5 dimensional descriptors, such as a layout. So we can use a structure line to describe the general spatial structures of the environment. We also can have the semantic segmentation labels for this environment. So we can label all the pixels that have the semantic meanings, have the ceilings, or region of ceilings, and the region of floor and beds. So there are multiple levels of scene descriptors for the scene image. So let's say if a generative model can synthesize such realistic things, does this model contains all the information? So it should contain all the multiple level information in order to synthesize such realistic things. So here we have a recent work, it's not recent, it worked last year, that tried to identify the causalities in the latent space for things synthesized. So basically, we want identify the causal effects relations between the latent space and the output space. The output space is a semantic space. So we have multiple label predicted, and then we want to correlate with the relations in the latent space. So we have this method called the high GAN to align the latent space with attribute space. So basically what we are doing is pretty simple. So we just sample a lot of images in the latent space, then throw into the generator, then we can get the image space. So we can have the synthesized image. Then we can get further get the attribute space by applying some of the shelf classifiers. Like previously, I built this places commonet, so it can output multiple level of attributes, such as thing categories, as well as multiple levels of thing attributes. Then we can have the attributes for the latent space. After we have the labels, then we can go back into the latent space and simply train some linear classifiers by training the predicted label as a ground truth label. Then we can get some decision boundaries inside the latent space. So it turns out linear classifiers can achieve about 90% accuracy for some binary attribute classifier classification, which means in the latent space, a lot of the attributes actually quite disentangle from each other. So for this particular example, you can see we get boundaries in the latent space that differentiates the nature lightning and the indoor lightning. So after we have these boundaries, there are a lot of interesting manipulation we can do. So let's say we have two samples. So there are 2 points in the latent space. So it synthesizes 2 images when we put into the generator. So like this. So because right now we have this boundary, then we can consider this boundary as the anchor, then push the latent code towards the boundary. Then we can change the attributes of the 2 images. So here we gradually push them towards the indoor lightning boundaries. Then you can see the lamp inside the 2 scenes just turned on. Also, more importantly, the global lightning conditions of the scenes also changed accordingly. So we can achieve such a realistic manipulation by pushing the latent codes. So here are some demos. So like here, you can see for the 4 synthesized image, there are lamps inside each one of them. So right now, I want to play a magic and turn up the lamp. So here is the animation. So we push the latent code towards the indoor lightning boundaries. Then we can magically turn up the lamp. And also the general lighting conditions have been changed. You even can see the reflection on the windows about the indoor lighting, also the shadows behind this lamp. So it's a very realistic manipulation when we like consider the latent space as a whole and manipulate it. So we also can get different attribute boundaries in the latent space. So like we can get wooden, non-wooden, and cloudy and non-cloudy. So each attribute will correspond to a binary boundary. So here is a demo video showing we adding clouds in the sky. So you can see those clouds in more like they just grow out in the skies. And also I really like the second samples. You can see even the sunset colors like shadowed on the clouds and even projected on the buildings. So it's very realistic manipulation. So here is another example. We push the latent code towards a vegetation attribute. So the trees and the grass more like automatically grow out from the scenes. And also for the first sample, you can see this generator is even smart enough to put a sidewalk on this grass so people can walk. So when we train the representation to synthesize the image. So the representation automatically discover this visual common sense knowledge and try to capture these different attributes. So it's quite amazing to see this latent code have represented such information. Another things we explore is that we further apply the method to analyze the layer-wise stochasticity. So previously, the GAN models such as DC GAN and the PG GAN have this stochasticity vector at the beginning. So basically, you have this random vector sample at the beginning and throw inside the generator and synthesize the image. But the STAIL GAN and STAIL GAN V2 have this layer-wise stochasticity design. So I think this is one of the most novel contribution for STAIL GAN. So rather than use the stochasticity at the beginning, so they introduce such layer-wise stochastics at each layers. So at the beginning, just a constant vector, and after each layers, they apply some random vector added on top of the features, then you can synthesize the image. So this layer-wise stochasticity, it can help the representation better disentangle the attribute at different level. So we apply our method to each layer's latent codes and analyze their importance. So here the plot on the left showing you the importance of each layer corresponds to the attributes. So here the horizontal axis is a layer depth. The deeper is closer to the image. The vertical axis showing the importance of the concept, such as at the beginning, those layers are more critical for the layout representation. So that's the middle layer, so it represents the object and attributes. And the later layer, the latent space more represents the color scheme. So it have this semantic hierarchies emerge from synthesized things. So this results actually correspond to our early work with Antonio on the object detector emerge, that we show that when we train a scene classifier, there is a semantic hierarchy emerge in the classification network. Like early layer, they represent the age, and the middle layer texture, object shape, the later layer than the object and the scene parts. So for this generative model, we can also see such a very nice semantic hierarchies emerge from the image synthesized without any external supervision. So here we show some results, like here we manipulate the attributes at the early layer, so change the layout of the environment. So here we also treat this layout as a binary attribute, so it can synthesize the views synthesize the scenes as a different view. So this kind of results is also relevant to the normal view synthesize. The difference is that we don't enforce a very strong 3D constraint here. So right now we just treat it as a binary attribute. But the amazing part is that when we train this generator, we don't have this pair data. Like we don't have 3D data. So the data we have, just those data downloaded from the web, they are totally independent from each other. So this generator just somehow discovers such a 2.5 dimensional representations for the things. So we can further go to the object, then we can, because the object is highly correlated to the category of the things. Like for the indoor things, like bedroom and living room, it's a furniture that decides the category of the things. So therefore, we can push the boundary towards the category boundaries. Then we can change the bedroom into a dining room by replacing all the furniture. So like we just move out the beds and cabinets and throw table and chair inside. Then we can change the category of the things. So this generative representation somehow nurse such a disentangle between the layout and objects. Then we can manipulate and change the category labels for the things. Any questions so far for this part? Or we can have QA at the end of this talk. Okay, so let's continue. So we further extend this kind of analysis to discover the latent factors in the face GANs. So right now we have this generator that can generate a very realistic face. But the trouble for this generator is that we cannot customize the output. Like we want a face with different angle and also a face with different age. So then we propose a technique called the interface scan at the CVPR this year to bridge the latent space with the attribute space for face synthesize. So the technology itself is similar to the high GAN. So we can discover various facial attributes, then we can push them towards the boundaries, then we can achieve such a realistic manipulation, such as make the sky cooler, then we can just throw a glass, make younger, then we can change the age. Then this lady wants to make me front faced, then we can change the angles of the face, and also for this, make me more man, then we can make this lady more man. Also, for the latent space analysis, there are a lot of amazing work in this direction, such as this work from Ali, Lucy, Philip, Isola. So they analyze the steerability of the GANs. So they also show that in the latent space, we can achieve such a geometric transformation, also some attribute manipulation. Also here is another work from Laurie, Alex Aldoliva, and Philip Isola. So they propose this amazing GAN analyzer for changing the image and memorability. So they can like tune the classifiers, and they can make this image more memorable. So this all those work have been looking into the latent representations. So I think that's a pretty promising directions. But all those previous work analyze the synthesized image. But what we want is just to analyze our own face. Like we can achieve such a facial manipulation, but what we want is just we want to upload our own image and manipulate the real image. So the critical issue here is how to edit our own image. So here so then we have this problem of GAN inversion. So GAN inversion, the objective is to invert the real image to the latent code. So we have the synthesize, we can synthesize image, but usually we want, giving a real image, we want to project this image back into the latent space. And then we have this GAN inversion problem. This GAN inversion problem can be formulated as a minimization problem if we just have the simplest case. So basically we want to optimize the Z, and therefore it can throw into the generator to synthesize the image. Then we can reduce the distance between the two. At first look, this optimization seems pretty easy to solve. So then I just let my student try my own face, because just looking at your own face, you can easily spot the difference. So I just put my own face inside, and I optimize these problems and get the latent code. And I throw this optimized latent code inside the generator. So let's have a guess to see what can be synthesized. So it's actually synthesized something like this. So it's reconstruct some face like this. So I think this generator already does its job. So let's put them side by side. So my face and the reconstructed face. So you can see this inversion, actually they recover the general structure of the face, such as the hair and the face color, the skin colors, but the identity is totally different. So it's just not me. So I just let my student try different random initialization. You know, the machine learning is more like a Chinese medicine. You should try different initialization and to make things work. So they just try different random initialization, but just get the result like this. So it's get a lot of this Caucasian version of me. So I can guess this result also shows the AI bias in the generator, because the generator is trained on the Cerebrate HQ. So this generator doesn't see so many Asian faces, because the celebrity in Hollywood, they are all Western people. So they don't have this Asian face in the database, so they cannot correctly recover, invert the Asian face. So this work, we also want such a debias the generators, like it can invert all kinds of face. So last year, there is this image to style GAN work that use extended latent codes to invert the image. So basically, they have this layer-wise stochasticity, then each layer will have its own latent code. So in that case, the dimensionality of latent codes have been greatly increased. You see, previously we have only maybe 512 feature vectors, latent vectors. Then we have number of layer times number of dimensions. Then the dimensionality greatly increased. So in that case, we can recover the image to some degree. So image to style GAN, this measure, work to some degree. So here I try my own face. So here is the inversion from a single code, 512 dimension feature vector. Here the inversion from image to style GAN. So here the latent dimension is 14 by 512. So it's much more latent space, larger space compared to this 512 dimension. Then we can recover this image in a reasonable quality. But it seems overfitting the target image. So we notice this overfitting issues. Like for this generator is originally just trained on human face. So here we try some long face image. So here we throw some cat face inside. And here is the image to style GAN result. You can still reconstruct the results to some degree. And we even try some like totally long face, like a bedroom image inside. Then this bedroom can recover an image like this. The images to style GANs can still recover the whole image. So this result clearly show that the image to style GAN just overfits the target image. So in that case, if the latent code just overfits the image, then we cannot use the inverted code do this facial manipulation. So here is one example. So we invert this image. This is the image to style GAN. Then we apply our interface GAN manipulation, like just push the boundaries in the latent space, like add smell and add glasses. So you can see the quality are pretty bad. So they just become very blur and very noisy, which means this latent code just overfitted on the single image. Then we cannot apply the discovered latent manipulation to the inverted latent code. So in that case, we want recover this. So this is just the issue showing that the inverted code may be out of the original latent domains. So you can see here we are solving a optimization problem. So this optimization problem is unconstrained optimization problem. So right now we just optimize the Z, then recover to minimize this loss, which means this inverted code, the Z, may not landed in the original latent space. Like we may end up with this rate point, which is outside of the original latent space. So in that case, we cannot apply our latent manipulation to those out of domain latent codes. To address this issue, then people further propose some encoder-based methods. So GAN compared to the VAE or autoencoder-based method, the GAN lacks this inference abilities. Then a lot of recent work that try to add some encoders to the GAN generator. So basically, they have this pre-trained generator. Then they just retrain encoder through this. So this is encoder approach work to some degree. So here I show some encoder results. So you can see first is this big by GAN. The method itself will not recover the image. They just propose a method to do representation learning, but you can see the reconstruction is not that good. Then there is a CVPR work this year, and they have this ALA, adversary latent autoencoder. So they can reconstruct the image like this. Then we have our recent encoder at ECCV that can reconstruct a face. but the reconstruction still far away from the real image. That's because we have this theoretic guarantee that we cannot recover all the image. Otherwise, we will get a very strong image compression method. So it will outperform the JPEG compression. So theoretically, it's not impossible to perfectly recover all the information just to use this encoder and the decoder-based method. So therefore, we propose an in-domain GAN inversion method by combining the encoder and the optimizing method together. So previously, I showed you that the naive optimization problem is just this unconstrained inversion. So it will end up with a code that out of the original latent space. So right now we have this in-domain inversion. So it's called the encoder-constrained optimization. So there is this second term. So you can see this reconstruct image will be encoded again by the encoder. Then it will throw back into this original latent space. Then we will try to constrain this. So you can consider this encoder as a regularizer. So to regularize this optimization process, just in case to make this latent code back into the original latent space. So with the constraints of this encoder, then we can optimize this. Then the latent code we have will be inside the original latent space. So here is a comparison with the image to style GAN method. So here is a side-by-side comparison with the image to style GAN. So the reconstruction quality almost the same, but the manipulation quality is much better. So here on the right, so we apply our interface GAN to the in-domain inverted code. Then we can decree the age and add smell and add glasses to this George W. Bush. So here are some demos. So we invert use this in-domain code, then we can manipulate those real face image. We can change the pose of the person. So here is we can just wear a glass. Also change the genders. Change the age. So here is another image interpolation result. So for the image on both sides, we just get their inverted codes. Then we can just continuous interpolate between the two images. Then we can have this very cool continuous interpolation result. This intermediate result is also a realistic image. We further develop some new applications. So this new application, I'm personally very excited about this. So it's called Semantic Diffusion. So it have been, so this is a new application, never been seen before. So this new application actually developed after we have this ECCV submission. So this semantic diffusion is that we have this background image. Then we have this foreground image. So right now we want just to copy and paste the foreground image on the background image. So if we just directly copy and paste, then we will end up with the result like this. So of course, the result is quite bad because there is discontinuity between the foreground and the background. Then we can further put this image inside this in-domain optimization. So what we are doing here is we just multiply a mask with this reconstruct image, which means we want reconstruct the foreground and let the background just automatically adapt it to the foreground. So the first term, you can see this mask will be just all 0 at the center of the image. Then will be all 1 at the center of the image. Then all 0 at the background regions. So therefore, we can just let the image reconstruct for their foregrounds and let the background automatically adapt it. So after this semantic diffusion optimization, then we can make the foregrounds and the backgrounds adaptive to each other. So you can see here on the right is this result after this semantic diffusion process. So we can keep this foreground the same as the input image, then backgrounds will automatically adapt it to the foreground. So you can see even the size of this sequence have adapted to the foreground. So here I would like to show you more results. So we have this a lot of backgrounds, and then we can do this semantic diffusion for all the image, like the Mona Lisa foreground, and we can optimize. I even try on my own face, so you can get some result like this. So from this, you can see the color of the background will be also adapted, as well as the shape and different, even the semantic parts have been adapted to the foreground. Like I really like my long hair version. So right now I'm growing my hair. So hopefully after maybe 6 months, I will have long hair like this. And even this sequence result also pretty realistic. So based on this, we have a live demo. So built on in-domain inversion on Colab. Here I actually want to show this lab demo to you guys. Let me share the screen. So here is this, so you can go to the project page, then you will get this Colab. So here, let's just run it. Yeah, this Colab seems very useful. So I just register as a pro, and I always get a V100 GPUs. It's quite nice. Okay, so we get a V100, one loads a utility function. So here is the semantic diffusion. So I guess Antonio already offline, so we can try his image. So we can just choose some image. So here I have an Antonio image. Here I just download Antonio's profile image from his website. So here, if we directly copy and paste, so you will see the results is really bad. You see, because the color, Antonio's foreground face color is quite different to the background. And here, let's see this star diffusion. So right now, it's star optimizing, and keep the foreground the same, and the background will automatically adapt it to the foreground. So here is our result. So you see after this semantic diffusion, so we can achieve a very realistic manipulation. So particularly I like this middle one, this Yashu Benju's version of Antonio. So maybe he should have a new hairstyle like this. Maybe this long hair is also good style for him. Okay, so let's come back to the, so I encourage you to try this live demo and let me know your result. Also this 2 minutes papers YouTube channel have a cover on this work. So it's very nice to see other people can reproduce our results and also make them excited. We can further adapt the semantic diffusion to scene homologization applications. So here for the same image, we also can do the similar operation, like we can copy and paste a new bed inside. So you can see if we directly copy a new bed inside this battery image, the quality is not good. Then we do this in-domain mask optimization. Then we can make the foreground and background coherent. And also here for the same image, we can copy and paste a new window inside. Then doing this kind of optimization, then the general lighting conditions will be very realistic. Then the whole image will be harmonized. So there will be a lot of potential for some computer graphics applications based on this. So based on all those previous works, we further released a PyTorch library called GenForce. So GenForce is a generative modeling for everyone. So this GenForce is an efficient PyTorch libraries for generative modeling. So we also released more than 60 pre-trained GAN models, also with this core live demos. So you can load the models, then synthesize the image. So that this library hopefully can support more interesting research in this generative modeling. There are some other recent work that's happening in this direction. So here is a recent work that worked with my students, Yu So we look into the unsupervised learning of latent semantics, because for a lot of the models, we don't have this supervised labels. Then we want to discover the meaningful directions in unsupervised learning way. So here we just propose very simple method, just looking into the first convolution layers. Then we can do this factorization. Then we can discover the semantic dimensions. So the demo on the right showing you the discovered semantic dimensions for those cartoon face, any face synthesized models. So this kind of method can be applied to other like a car and oil painting models where we don't have the attributes. So we also extend the generative modeling to a wider perspective. So here is a recent work, just a very new work we just submitted last week. We apply the generative modeling to improve the generalization capabilities of end-to-end driving. So if you know reinforcement learning, so in reinforcement learning setup, so usually the agent is trained and tested on the same environment. So for this end-to-end driving setup, then we have this one map. Then we just train this agent many thousands of iterations, thousands of episodes. Then we can have a car that can run in the same environment, in the same map, and without any problems. But the issue is such model that trained on the same map have problems for the generalization. Like when we apply this training model to another map, so here is the result, tested this agent on another map, then this agent is more like get drunk and have this car accidents. So which means the generalization of this end-to-end driving is really a problem. So in this case, we can use generative modelings to improve the generalization of the end-to-end driving. So basically, we first define some primitive traffic blocks. So those traffic blocks like the streets, ramp, fork, roundabout. So we have those blocks with configurable settings such as the number of lanes and also the traffic or radius of this road. Then we have these blocks. Then we propose some procedural generation. So the procedural generation is a mechanism that commonly used in a video game. So it can use to generate different game levels. So we use this defined traffic blocks. Then we can use some search-based procedural generation, then synthesize a lot of different maps. So here show the map generation process. So it's like a depth-based search method. Then we can assemble the predefined traffic blocks and combine them into the maps. So follow this procedural generation. So we can have a lot of generated map. So here on the right, it shows all the generated map following this procedure generation. So all those maps can be further turned into training environments where agent can just interact with the environment and learn how to drive. So here is a experimental result. The horizontal, so the first row shows training performance on different training maps. The second row shows each agent's test performance on 50 holdout maps. The green regions showing the successful episodes. So you can see here, if we just train on one environment, then on the training performance is very high, so we can get almost 100% accuracy. But for when we deploy this agent on our holdout test sets, the performance, so gradually we can increase the number of maps in the training set. So here we have 6 procedurally generated map in the environment. Then the performance on the test set start improving. You see here the performance, the green region get improved. And later, after we include 100 procedurally generated map, then the generalization ability of this agent can be greatly improved. You see here, right now, the performance on the training set is almost the same as the performance of the agent on the test set. So that shows the generalization ability of the agent being improved. So you can see in reinforcement learning, the generative modelings can also be adapted and used to improve the machine learning agent. So here are some further demos. So we have this trained on a lot of procedural generated map. Then this one single agent can handle all different kinds of maps. You see here we have 6 different maps. So this end-to-end trained agent can brake and avoid the accident and finish this driving task on each of the environments. We show this when we apply this generative modeling to augment the training environments, then we can improve the generalization abilities of the end-to-end agent. Okay, so here finally we come to the end of the talk. So I would like to acknowledge my students. So Yu Junshen, Chou Yuanyang, and Jiapeng Zhu, and Yin Hao. So they work on this Gen Force, have done tremendous work. So we push these directions for generative modeling. So we have this Gen Force web page. So the Gen Force is actually shorted as a generative force. So we have this slogan, "May generative force be with you," from my favorite movie, Star Wars, because I believe the generative force could be very important to the computer vision and machine learning. So we have this generative approach to the problems can be used to improve the previous classification-based method. Okay, so that is the end of my talk. So may generative force be with you.
Thank you, Bolei, for the great talk.
Mm-hmm. Yeah, if you have any questions, so you can ask.
I have a question. Hi. Oh, sorry, go ahead.
Oh, sorry. Hey, Bolei.
Hey, Jenny.
That was a fantastic talk. That was so wonderful. I was wondering if you could give me an impression of how you might feel about mixing generative scenes with regions of a photograph that you want to remain static. That I thought like the continuation from the scene attribute manipulation to the face manipulation might show that like in a real photography setting that you might want to, I don't know, treat faces or people or foreground objects differently from the background. And yeah, if you had any thoughts about how that would work into your frameworks.
Yeah, I think that's a very interesting application. For this general photography, the problem is we may not get the reasonable good generators. So, you know, our work, we have to have train up generative model But current generative models only work on those limited domains, like you already collect all the face image or all the living room image or bedroom image. But if you just want to train a very generic generator, like on all the nature like things, it may not work so well in this case. But I think you can take a look at this P2P based method, like P2P based method, like pioneered by Jun and Yang, that they can directly input the real photography and output the manipulated face. So they're actually a combination between our method with the P2P. Like we can use our method to generate the annotated images, like paired data, like the person smell or non-smell for the same person. Then we can collect this paired data, then treat those paired data as a training data for P2P net. Then that may can help you manipulate the real photography.
Fantastic, thanks so much.
Yeah, sure, thank you.
So that was an excellent talk. Hi, that was a great talk and very neat work. I had a question about the diffusion stuff that you were doing. I was trying to figure out from the pictures sort of what's taken from the foreground and what's taken from the background, and it's not totally clear. You know, like in the face case, it sort of loses the actual background, but maybe because the background is not, the actual background scene is not generated very well by the model or training.
Yeah, so for this semantic diffusion, so you can consider this process more like we want to preserve the foreground. Then, so it's more like a diffusion process, and the information propagates from the foreground to the background. The background will adapt it to the foreground. But sometimes the background, so like the real background, I mean, the background is behind the person. So those backgrounds sometimes will be affected. So this result, you can see some of the background, like real background, like those white regions will be affected. But I think we can apply some background removal techniques to preserve the actual background. That's what you mean?
Yes, exactly what I mean. And for the bedroom scene, it was a little less clear, I guess, what was I guess it still seems like more is of the layout and things are still taken from the foreground as opposed to the background. So I guess what, you know, for diffusion, what can you say you're preserving when you diffuse the foreground into the what's left? What are you preserving from what's left?
Like for the face example, it's just the identity we preserve. Like people have very sensitive feelings for the identity of the face. So then that's the foreground of the person. Then we want to preserve the foreground, the identity of the person. The background can be adapted to the
What about on the left here? What are you preserving and what's changing?
You mean for the same image?
Yeah, you're changing the bed, but it also changes the layout. So is there, I mean, I know it's a little fuzzy, but can you say sort of, this is the type of thing that's being preserved? Can you make an observation?
Yeah, because some of the foregrounds, there are some layout information inside this foreground. Then the layout information will be carried out into the background. So, but we can like reduce the size, like in our collab demo. So there is a parameter we can change the crop size. So if you have a smaller crop size, then you only have the appearance of the foreground. Then it will just preserve the appearance. But if you include more information, like even you include some like floor here, even some structure line here, then it will carry this information to this optimization process. Then this information will be like diffused out into the background.
Right, and maybe here part of the issue is that the bed's in a different pose. So you can't just replace one with the other because the pose is not, you're not allowing the pose to change, right? You're just putting the exact bed in there with a different pose. So it has to change the layout to match.
Yeah, exactly. For this scene manipulation, it's much more challenging compared to face because this layout will also have to take into consideration. Like if we just replace like another angle of the beds, then the optimization result is not that good. So we have to like align the two parts for the scene manipulation.
Thank you.
Yeah, sure. Thank you.
Hi, Bolei. So maybe I missed it, but when you are optimizing Z with the encoder regularization, the encoder, I assume, is already trained?
Yeah, the encoder is already trained.
So what does this? Yeah.
Encoder is trained, just follow the. So encoder just trained using a similar method. It's more like we have some real image or synthesized image, then we can throw the encoder and train this part.
So if you fine tune later the encoder with that objective, like that doesn't make any sense to do that, to like speed up the latent vector, like.
Yeah, I think if we also fine tuning the encoder can be improved. But here we just keep two stage, like first train the encoder, then just keep a generator and encoder fix, and just optimize the Z.
I see. And another question on the work at the beginning where you're showing like the different latent presentations by training binary classifiers, there is one like feature that is like the layout of the room. So what is the classifier that you use there?
Oh yeah, so that's a good question. So for the layout, we actually borrow some layout predictors. So it will capture the key points. So it's like pose. Then we just select one kind of layout. Then we just use a central line to quantify this. Like if the central line on the left half, then we will label class 1. If the central line is on the right, then we will class 2. So we just consider this case. But the layout structure manipulation is more complex than that. So we have some ongoing work that just specialize in this layout manipulation because it's relevant to this novel view synthesized work. So we want better handle this. But in our high-gun work, we just like have this heuristic, just like by force, just use a binary labels for that.
I see. Thank you.
Yeah.
Are there any other questions for Bolei? Okay. If not, thanks a lot, Bolei, for this great talk. It was great having you.
Yeah, great. Yeah, let me know if you guys have any questions. So you can drop me an email, and we also have some one-on-one meeting later this afternoon, I think. Yeah, we can chat.
That's right.
So hope everyone can have a wonderful social distancing. Yeah, let's see what's